Okay, I want to go over some practice problems for the upcoming test. Now, notice I started off, I asked you to state the mean value theorem, and you just want to know that by know that word for word. If a function is continuous on a closed interval and differentiable on the open interval, there exists a c in the open interval such that f prime of c is equal to f of b minus f of a over b minus a. So we've talked about that before, but know the mean value theorem. Now, then we need to know how to apply it. So, or at least, work with it. So here we've got a function 1/2 x squared, and we want to know, does the mean value theorem apply? Well, this function right here is continuous and differentiable every place. It's a polynomial, so it is continuous and differentiable on this interval. So what we need to do is we need to find the c so that f prime of c is equal to, well, let's see here, 1/2 5 squared minus 1/2 3 squared over 5 minus 3. In other words, we've got to do that. Now, in place of f prime of c, let me go ahead and put the derivative. And the derivative is x. So that's pretty easy. So x, f prime, well, f prime of x is equal to x. So we're just looking for, basically we're just plugging into this thing. We got 25 halves minus 9 halves over 2. So I guess that's going to be 16 halves over 2, which would be 16 fourths, which equals 4. So the answer is 4. So that one was pretty easy. That one fell out really quickly. Now on this one, we've got x to the 4/5. Okay, so now this looks to be continuous on this interval, right? But from -1 to 3. Let's see if it's differentiable. Let me find the derivative here. The derivative is 4/5 x to the -1/5. So we've got 4/5 times 1 over x to the 5th. Now this is not defined at 0. So 0 is in this interval between -1 and 3, so this one does not apply. So we're done with that. The mean value theorem doesn't apply there. Okay, now let's go through and see what we can do with this function. We've got a function and we want to find the critical numbers. Okay, the critical numbers we find by setting the derivative equal to 0. So we want to take the derivative of this function, which this is an easy one, and just set it equal to 0. So let's see what we've got here. Maybe it will factor. X minus 1, x minus 4. So we get critical numbers to be 1 and 4. These are our critical numbers right there. Now remember, we also find critical numbers by finding where the function is undefined. Set the denominator equal to 0. That's not something we have to worry about here. Now we want to find the intervals over which the function is increasing. So let's see here. We've got 1 and we've got 4. I'm going to pick test numbers from each region, maybe 0 over here, 2 here, and 5 here. And I want to plug those into the derivative, which is x minus 1, x minus 4. Okay, so I'm going to plug in a 0, a 2, and a 5. Now, if I plug in a 0, I get a negative times a negative. That gives me a positive. So in this region, the function is increasing. Now, if I put in a 2, I get a positive times a negative. That's a negative. So it's decreasing in that interval. And if I put in a 5, I get a positive times a positive which gives me a positive increasing. So look, the function is increasing where the derivative is positive. So that's negative infinity to 1 unioned with 4 to infinity. Okay. Now where is it decreasing? Well, from 1 to 4, where it's negative. Now, the x value is at which f has a maximum. Okay, so we're using the first derivative test. The function was increasing, and then it started to decrease here at 1. So there's a maximum at x equals 1. It has a minimum where the function was decreasing and then started to increase. So there's a minimum at x equals 4. Okay? Whoops. Okay, got to slide this down. Now, the intervals over which the function is concave up. Okay? Well, that's the job for the second derivative. So I take the function and I find the second derivative, 2x minus 5. And I'm going to set that equal to 0. I'm kind of doing the whole process over. So I set the function equal to 0, and what I get there is a possible point of inflection. So I'm going to make a number line, put a 5/2 here, and pick a number to the left, which I'll pick 0, and a number to the right. I guess I'll pick 3. And I plug that into the second derivative. If I plug in a 0, I get a negative. If I plug in a 3, I get a positive. So the graph is concave up from 5/2 to infinity, and it's concave down from negative infinity to 5/2. So where it says concave up, I'm going to put 5/2 to infinity. Where it says concave down, I have negative infinity to 5/2. And the inflection point occurs at 5/2. So it would be 5/2 comma f of 5/2. That would be the inflection point. Okay. Now, let's see what's next here. Okay, so that's that. Now, we could use the second derivative test also. If we took these critical numbers that we had earlier, 1 and 4, and plug them in, if I plug in the 1, notice I get 2 minus 5, and I get a negative. A negative second derivative at a critical number indicates a maximum. If I plug in the 4, I get a positive, indicates a minimum. Okay, so the first of these is a word problem that involves trying to find the optimal area for print when you're confined to the page. Here's the page, and you're confined to the page being 90 square inches. So I think what I would do to start off this problem, I would just go with what I'm given here. I'm given that the page contains 90 square inches. I will call the horizontal X, and the vertical I'll call Y. So we've got this. We've got XY equals 90, like that. So that's my constraint. Now the other part, we have to find the objective. So we're told that on the sides and at the bottom we have 1-inch margins. At the top, however, there's only a 1/2-inch margin. So if I wanted to come up with a formula for the area of this printed area, it would be like this. It would be, okay, I've got this width here, right here. This is going to be X minus 2, see? Because I take 1 inch off of each side, times the Y. The Y is not going to be minus 2. It's going to be 1 here and a 1/2 up here. So it's 3/2. And that's my formula for area right there. Now what I want to do is I'm I need to use this constraint to get rid of one of these variables. I think I'm going to get rid of the y, so I'm going to say y equals 90 over x. See? So now I have this. I have a of x equals x minus 2 times 90 over x minus 3/2. And that's what I have to differentiate and set equal to 0. That one right there. Okay, now I think before I plunge in here with differentiation, I think what I want to do is multiply this out. You don't have to, but I think I'm going to go ahead and do that. I'm going to take x times 90 over x, and that's just going to be 90. X times negative 3/2, that's negative 3/2 x. See? And then I multiply the negative 2 through, and that's going to be negative 180 over x. And then positive 3 when I multiply negative 2 times 3/2. Okay, so there's what I have so far. Now, I'm going to, I guess at this point I can go ahead and differentiate. I don't guess I did anything wrong there, did I? Just double check. Yeah, looks good. Okay, the derivative is going to be negative 3/2. Now, I got to be careful. This one, and I should have done this first, this is 180 times x to the negative 1. Okay, so I'm going to bring the negative 1 around front, and that's going to make that a positive 180 x to the negative 2, like that. See, I kind of jumped the gun differentiating before I set it up where I could use the power rule, but this is the derivative. Okay. Now I want to set this equal to 0. So I've got this. I've got 180 over x squared equals 3/2. See, if I just set it equal to 0. I guess I can reciprocate both. So I've got x squared over 180 equals 2/3. Now multiply both sides by 180, and I get 2/3 times 180. Okay, 2/3 times 180, and that will be, let's see here, 180 divided by 3 is 60, so this is going to be 120. 120. And then I want to take the square root. So the square root of 120 is 10.95. We'll just call it 10.95. I guess I'll do 3 decimals. Okay. So there we have it, 10.954. That's what the x needs to be. In other words, that's this length right here. Okay. Now I need to find the y. Remember, the y is equal to 90 over x. Well, let's see what that is. That's 90 divided by the square root of 120. And let's calculate that. 90 divided by the square root of 120 would give me 8.215. I'm just truncating three decimal places. Okay, now if we multiply these two together, we should get very close to 90. Okay, because I mean, I did some rounding here, so we're going to be off by a little bit, but you can kind of check where you are there. Now we've got to determine what the dimensions of the page are. Well, this dimension here is going to be 10 0.954 minus 2, right? By the y is what was the y? Oh, 8.215 minus 3/2. So there it is. That's the dimensions of the reading area. So see, notice what we did. We labeled our constraint. We knew that the length times the width of this page was 90. And then I use that, my assignment of the variables here, then to represent the objective. How can I model this using this x and the y? Okay. Now, so this is a typical optimization problem. Now we've also got these related rates. So here's a related rate problem. Okay, so you have this situation where a 7-foot stretchling, he's a stretchling, 7 foot, walks away from a 21-foot light pole. So he's 7 feet tall. The light pole is 21 feet. Okay. He's walking away from the pole at 5 feet per second. So I'm going to label the distance from the light pole to be x. So this right here is x. And the rate of change of x is going to be 5 feet per second. Okay. Now, they want to know, well, how fast is the length of his shadow changing? Well, the length of his shadow is this right here, and I'll call that y. So we want to find dy dt. Okay, that's what we want to find. Okay, and then another question is, how fast is the tip of his shadow moving away from the pole? Well, the tip of his shadow is this, and the distance is x plus y. So we also want to find d dt of x plus y. Okay, so what I need to do then with these related rates problem, I need to find a way to relate the known to the unknown. And that way I can relate the known rate of change to the unknown rate of change. So I'm going to do that in this case by noting that I have similar triangles here. So I notice that 21 is to x plus y. See? This big triangle. This side is to this side what 7 is to y. Okay, the big triangle is to the little triangle. Now, let's see what I can do then. I cross multiply here and I got 21y equals 7x plus y. That means 21y equals 7x plus 7y. And that would be 14y equals 7x. Like that. And look, I can do more. I can divide out the 7. And I get 2y equals x. So now I know how x and y are related. Now I can differentiate. 2y prime equals x prime. Well, x prime is 5. So I've got 2y prime equals 5. So y prime is 5/2 feet per second. Well, that was easy. Now I can go up here and I can talk about how fast is his shadow moving away. So that would be x prime plus y prime. And that's just going to be 5 plus 5/2, which would be 15/2. Yeah, that's it.